everybody in a different class period, and everyone here and anyone absent who's watching this at a later time. Sorry, Ryan Union, say it one more time. What did you guys just receive back?
Our T-proof grades and our formulas.
Yeah, so we're going to go over questions in section 6.2 in just a second. So for those of you that are bored or you already know everything about this test, feel free to open up WebAssign and get number 13 and 14 ready. Those are the two we're going to look at. But let me go ahead and give you some quick reminders of the last test. That WebAssign portion, once again, for a few different reasons, I have not been able to process it yet. But Friday afternoon, you guys get a minimum day, right? And I get a work day. Thank you, Jesus. Because we have like a campus preview, something on Saturday. Anyway, I'm going to be working on just like going through all my, I think I have like 150 now, maybe, no, I think I got down to like 75 emails of students turning in late work. My Algebra 1 kids are now on Google Classroom, which means I get tons of notifications from them turning in things late all the time. So it's kind of bogging me down a little bit until I get into a new groove. But, what has been processed for your Chapter 5 test grade, once again, reach out to regular pre-cal, get some tutoring hours in, quiz them on the basics. They only are being tested on 5.1, 5.2, 5.3, not the crazy formulas from the end. But your guys' test had 3 parts. Part 1 was from the minimum day, and that was the T-proof long answer portion. You had blank paper and you had problems. There was up to 16 points on that. Then you had a formula portion. Well, technically, I guess then you had a WebAssign portion. We'll figure out what that is as far as how many points you could have gotten there. And then number 3 was the formula portion. Does that make sense, guys? That we had this like in little bits and pieces, right?
Yes.
Okay, so the formula portion. Okay, and that one was what you guys also just got back. You got back number 1 and you got back number 3. These are the ones that you guys gave me like paper copies, and they have been graded and they've been put on Google Classroom for you guys to see. This one was up to technically 16 points, but up to 15, and there was a +1 bonus opportunity with that last half angle property. So 15 plus 16 is 31. There's up to 69 points here possible. Some of you guys know what your WebAssign percentage is right now, right? So if you want to see what your overall test score is going to look like, it's out of 100. And then some of you are remembering that there was a bonus opportunity, right? But that's technically not going to be in the actual grade itself on RenWeb. That is going to be in an out of 0. I think that was up to Jackson, 3 points bonus, right?
Yeah.
So you could have gotten 3 points out of 0, which as a fraction doesn't make sense, but like in RenWeb, 0 points possible, 3 points is what you could get. That's where bonus shows up on RenWeb. But that bonus opportunity is separate. If you want to know what your percentage is or your grade is, all you got to do is figure out what is my T-proof score plus what is my WebAssign score plus what is my formula score. Now check it. Don't add the percentage times 69 because that's how many points came from WebAssign. So if you want to figure out what your score is, you can take your T-proof, how many points did you get there, plus your formulas, how many points you got there, plus, like someone in here got like a 91 on that WebAssign. It was awesome. So take that 0.91 and multiply it by 69. Or whatever percentage you got on WebAssign. Now, what's the good news is I still need to process this so that there probably is more partial credit coming. So what you're doing right now is you're calculating the worst your score could be. Because WebAssign doesn't know partial credit, and I do, right? WebAssign doesn't get partial credit, and I do. So there is more partial credit coming, and that's what I need that work day on Friday for a few different classes to get online and to do that partial credit for you. Maybe I can do it sooner. Monday nights are my grad school class, so I have a lot of homework due on Monday nights. Weekends, I get somewhat caught up. Like the papers that I got graded. I don't get all the way caught up until later on in the week. So your worst case scenario of your test is how many T-proof points plus how many formula points plus your WebAssign percentage times 69 If you want to, you can think about adding those bonus points if you got that submitted on Google Classroom, and then realize that's the worst your grade could be, and it's probably going up with partial credit as long as you attached work on Chapter 5 in Google Classroom. Any calculation questions? Jackson?
Does the +3 bonus count? Like, does that help your grade more if it were like separate? Or?
No, it's the exact same thing. Because I have RunWeb calculating like in a category like tests and quizzes. It just says, give me all the points, give me all the points, give me all the points that they got out of all the points that were possible. So like a 100-point test is worth more than a 10-point quiz. So this is literally just adding 3 into the mix like it would have done if I'd done it separate. I just like parents seeing like, hey, they're taking advantage of bonus. They're not taking advantage of bonus. It's nice for them to see sometimes. Is that cool? Have my calculator out and ready for our problems that we're going to go over. WebAssign 13 and 14. You guys have them out and open? Any more calculation questions? Any more calculation questions? Okay, cool. This is worst case. Partial credit is coming. Remember, WebAssign says you were all wrong. And I say, oh, look, you got something good. Let me give you half credit back. That's the worst case scenario. Ryan Kokorian. Move the decimal place 2 places. So if you had like a 91%, put 0.9. 100%, 1.00.
Is there like a way you can put it out of this?
If you want to, there's a button called Catalog Vars. I think it's like a second. Can anybody find Catalog Vars? I think it's at the bottom. Is it second negative or second zero? Second zero? That gives you every single possible calculator function that is built into the calculator. So if you want to scroll through, it's alphabetical. But I don't know if you'll find anything. It might not be there. Yeah. You could also do divide by 100. You know what I mean? Like 91 out of 100. You could do that. Yeah. All right, cool kids. Here we go. Homework number 13. Hold on, pause. How many of you guys want to look at homework number 13? That's it? Maybe we'll do it at the end of class. Who wants to look at number 14?
Yes.
All right, hold on. Should we do a vote one more time?
Yes.
Tell your classmates to listen up.
Everyone listen.
How many of you guys want me to go over 13? Raise your hand. Oh, you do want me to do this. Okay. Here we go. I was just saying, if you don't want me to, we're not going to waste class time. Here we go. 13. Let me show you the hardest part of this problem. It's called, what is a bearing? Has anybody ever heard we need to get our bearings? What's it mean? Anybody who's heard that phrase, we need to get our bearings. No, not in the math homework, just in general. If someone says we need to get our bearings, I'm getting my bearings. Hold on, let me get my bearings. What's going on?
The rotating ring. No, man, she's speaking of the phrase.
The common phrase. Johnny Colmorgan, help us out. What's it mean to get your bearings?
You're getting ready to go in that direction. Oh, it's like getting ready. Like, oh, we're gonna get
Putting your head on.
Cross country team, when you head up to Mammoth, or if you can imagine heading up to Mammoth, or something high elevation. What's getting your bearings? It might not be like popping out of the van and then going for like a 10-mile run.
getting settled.
Maybe like letting your body get acclimated. That could be one way of getting your bearings. Another way is like in direction. If you're like in the woods, maybe you have a place that you're kind of familiar with, but you're like, well, hold on, let me get my bearings. You're looking at landmarks, you're trying to be like, where am I? Oh, here I am. Let's go this direction. It's the idea of considering your surroundings or getting acclimated to your surroundings to be able to make a wise decision. What does bearing mean here? Kiddos, if you're lost in the woods, and you're trying to get out, and let's say you don't have, like your GPS isn't coming up. So your Waze isn't coming up, your Google Maps isn't coming up, you don't have enough of reception, you don't have enough reception to be able to get a navigation app up. What is technically the only thing you need to work on your phone in order to be able to get your bearings? How do you get your bearings? Lost in the wood. The navigation apps are not coming up. A compass. To get your bearings. I'm not saying to necessarily make your way home, but to get your bearings, you just need a compass. What will a compass allow you to do? North, south, east, west, and allow you to not keep going in circles, right? If you're lost in the woods, what do you not want to happen?
Get attacked by them.
Well, that also.
Have your phone down.
But you want your steps to matter. And in order for your steps to matter, what do you not want to be doing?
Walking in a random direction in circles.
Going in circles. If you're going in circles, you're wasting energy and you're not going anywhere, right? At least if you could head one direction, or if you could head the direction of what you think is the populated area, if you have a compass, it'll at least let you head one direction. Now, thinking of that, when we see bearings in navigation, literally we're thinking of, hey, Phoenix is north, south, east, west, Minneapolis is north, south, east, west, and Albany is north, south, east, west. Hey, didn't they say that Albany was due east, like exactly east of Minneapolis? Oh, it doesn't say that Albany is due east, but instead it says that Minneapolis is exactly due west, which means it's directly across from. There is no angle of inclination. You go straight west, pull out your compass, make sure you keep on going west. If you walk long enough and you can like swim some different channels of water, some different lakes specifically, you'll make it. Okay. So when it says bearings from, hey guys, what does from mean? Is that the ending point or is that the beginning point? So does it make sense why I have north, south, east, west on Phoenix? Phoenix is my beginning point, and I am trying to head towards Minneapolis or head towards Albany. So when it says get your bearings, many of you should have been able to solve for, I'm going to call this angle P, I'm going to call this angle M, and I'm going to call this angle A, just thinking about Albany, Minneapolis, and Phoenix. You should have been able to solve your triangle, right? You have side, side, side. What law would you guys use? Cosines, because cosines is great with three sides. You can say cosine of A is equal to, or actually cosine of P is equal to, cosine of A is equal to, cosine of M is equal to, and use the other side strategically. You should have been able to solve your triangle. What was the tricky part was probably, how do I find my bearings? Any Boy Scouts in here? Any Girl Scouts in here? Or anybody just in general know what north degree east is talking about? Where are you starting from? If you're on the ocean, you can start from the North Star, and if you have a compass, you can start from where it's pointing north. You say, where is north? Ha-ha, there it is. That's not where north is for us. Obviously, north is more, this-ish direction. There's the 5 north. Is it here-ish? It's a little rough. Someone pull out your compass app and tell me exactly where north is. It's up there somewhere. Because I live north. I think so. Mine does. Oh, see, I was close. I was this way. Is it there?
I think north.
Someone pull it up. Someone pull it up. But Phoenix has its north here.
Bro, but Jackson. Yes.
Anybody find the compass app?
Read it down.
South.
We're gonna prove Jackson.
That's not south.
So is it like
South is south. Oh. You need to go.
it's right here. It says it's here.
Jackson, they put like a real compass inside the
They do?
Oh, I think it's you holding your phone.
There's no magnetic.
It says north is here. Exactly.
Yeah, no, it's not this way.
Missy, you're going north. You're like in north.
North is directly behind me.
Yeah.
I'm just trying to figure out Ryan's app. Do you like flip it this way? Why would you flip the app around?
I thought north was there.
Because he's right here.
You see the M on the board? On like the wall sort of?
Directly behind me.
Forever? And
So it's like going the opposite direction.
that's like basically directly
It's not north.
No, because remember
It's like
it's
40 degrees off.
Coach 1, like you get north, that's 1, right? North is
So we
1,
want to go
and then like 3, and then 4.
I also
Basically, when the sun is out, the shadow is looking at 4. So then it would be like 3, 2, 1.
Also, we're
Andy, how's yours working?
There we go.
Ryan, I think your settings are off, but I don't know why then.
Bro, I downloaded
Is that it? Ryan, are you on Wi-Fi or are you on data?
Oh, Joey, there. Now it's facing.
But it's deep. Say you turn it on airplane mode, wouldn't it like stop? Right, because your phone doesn't have the magnetic thing.
Oh.
Bro,
That's why I was like, if you had a depth,
Ryan, yours is
just
messed up. Yeah, it says north is there.
oh my god.
That's right. This is doing it with the back.
Hey, it works. Mine says
Bro, my phone is on airplane.
Yeah, Ryan's is.
And my wife is off.
north.
You're just gonna get like a.
It's a compass.
Oh.
It's directly opposite for some reason. There must be a setting or something. You can have. Okay, anyway, sorry. All that to say, the bearing says in Phoenix, if you could find north, that is this whole true north, we're not going to do that. But if you can find north in Phoenix, where or how would you turn east? How much would you have to turn east from that north in order to be able to head to Minneapolis or to head to Albany? So, for letter A, what you would want is this awkward outside the triangle, well, that stinks, angle. For A, you would want from north, turning east to get to Minneapolis. Now it's like, well, how the heck do I find that? Check it. I'm going to show you with geometry. And I'm also going to show you why we don't spend a lot of time in bearings, because this isn't a physics class. But hold on. If I was to, ready? Focus. It's all about geometry. This is the exact reason why in section 6.3, where we're headed, we are not going to stay with triangles. We're going to try to find another method beyond triangles to deal with vectors, because triangles get tricky. And what I'm about to show you is something to do with parallel lines. Oh, geometry. And transversals that cut through that parallel line. Oh, geometry. Or if it's more fun, I also emailed you an answer key this morning. For grading calculus purposes. All right, ready? In geometry, you guys learned that there are parallel lines. Everybody's been watching the video. P.S. We've been playing with the compass app. These are parallel lines because it's the north, south, east, west. We're not talking about spherical geometry. We're talking about just in general geometry. They're going to be parallel because the north-south line is going to be parallel on either, I guess, latitude, you could say, of those two cities. Now, if they are parallel and cut by a transversal, I should be using a different color for this. If they are parallel and cut by a transversal, we know that same side angles will be supplementary. That means that this angle on this side of the transversal and this angle on this side of the transversal, they're not congruent. So I'm going to mark this with like a different line so you know that they're not the same angle, but they do add up to be 180. And I know that this guy is 90 degrees because they said due west. So I know it's 90 degrees there. So check it. I can say that 180 equals my 90 plus A from this side. From geometry, interior angles on the same side are supplementary. Alternate interior angles are congruent, but same side interior angles are supplementary. Supplementary means adding up to 180. 180, take away the due west, 90 degrees. Take away the angle A that you should have already found from solving your triangle. And then I can also say plus angle P from solving your triangle, and the one that I want, which is X. I'm trying to find the bearing. All I have to do is 180 minus 90 minus A minus P, and I will get the bearing from Minneapolis to Phoenix. These two parallel lines with a transversal cutting them form supplementary angles that are a combination of the triangle and whatever's going on as far as my north, south, east, west. This guy's bearing is kind of easy as far as northwest is 90 degrees. What's outside the triangle? For Albany to Minneapolis, it's north, 90 degrees west, or a better way of saying that is just head west, head straight west. I'm trying to find this unknown poor little guy right here for my bearing down here. So if you've solved your triangle, it's easy cheesy. X is equal to, once again, 180 take away 90, that's 90, take away A, take away P, and you have your bearing. And all that's different for letter B. All that's different for letter B is I don't want to head to Minneapolis from north. I want to head to Albany from north. So all I have to do is just X plus that little, no. What's that angle in the triangle? P. There we go. So solve your triangle and then plug it into those little baby formulas and you will have your bearings. Solve those triangles, plug into those little baby formulas, and you will have your bearings. If you can make a note to yourself, I think it's due by what, 3:30, 11:59, something tonight? That's slide number 9. Slide number 9. If you solved your triangle, it was easy, and solving your triangle was just law of cosines. Slide number 10 is number 14. Slide number 10 is number 14. If you need me to go back for like 30 seconds, I can go back for 30 seconds. If you want to take a picture of it, but it's also slide number 9 in the Jamboard. You guys should have already solved your triangle. That was the easy part. Law of cosines. Solve your triangle, and then all you gotta do is throw it in these relationships I found from geometry. Okay. Number 14 also has a triangle. I could kind of blow him up a little bit if it would help. He's kind of a tiny triangle. We have a theta right here. We have a 1.5 measuring right there. We have a 7 inches measuring right there. And we have an unknown right there. It wants us to write an equation that relates everything. Well, guys, an equation that relates everything. And it says specifically giving the relationship between x and theta. We technically have two options. Do you guys want to do 7 squared equals, or do you want to do cosine of theta equals? Wait, pause. You know that both of these are law of cosines, right? Looking in your notes, don't we have like the b squareds or the c squareds equal and the cosine of c equals, right? So which one do you want? Just tell me and I'll go for it. Okay, so cosine theta is equal to, remember, take the other two sides. So that'd be x squared plus 1.5 squared minus 7 squared all over. This isn't magic, it's just the math, right guys? If you want to, I'm sure you can make that a little bit prettier. If you want to, I'm sure you can make that a little bit prettier. If I was to go ahead and swoop that away real fast, oh hey, all they did is get everything equal to 0. So all I gotta do is move everything to the other side. Everything as in, I can multiply both sides by 3x. Isn't 3 the same thing as 2 times 1.5? Multiply everything times 2 times 1.5 times x, which is 3x. Then I can go ahead and get this guy on the other side. We're kind of getting it into like a standard form. And the standard form says, hey, get me equal to 0. And it's like, all right, fine, whatever. So getting them equal to 0, I have x squared as my quadratic piece. I have minus 3x cosine theta as my linear piece, and then I have, I don't know, whatever this guy is. 1.5 squared minus 7 squared. I'll let you guys figure that out. For your other piece, and that's going to be your equation. Boom. Shakalaka, I got it. And then it just says, get x alone. You're like, get x alone. Andy Tadros, do you remember that really weird formula with the square root we had to use the other day to get something by itself? Remember, like, I was putting, like, c equals, and it was really like an x equals, but I couldn't make it an x.
We couldn't make it an x. Quadratic.
Yeah, the quadratic formula, right?
Okay.
This one, though, I can make it an x, because that's my actual variable. So when I start putting in random things, like, x equals negative b, I don't have to worry about that whole ABC thing, because I totally have no ABCs to get in the way. So there's my A, there's my B, here's my C. All I need to do is plug into the quadratic formula. B squared minus 4AC all over 2A. And then you'll have it. Oh, they say select the sign that yields positive values. I'm pretty sure that I'm going to need a plus and not a minus. If I do a minus, that is not going to give me positive values. So then for that, I'm going to use the plus and not the minus. You guys are wondering if you'll see a little quadratic formula if I quickly look behind the scenes. Yeah, you will. That's a quadratic formula. You can write it different ways, but really fast, just in case you're not getting it from my underlining. A is equal to 1. B is equal to negative 3 cosine theta. And C is equal to, I don't know, whatever 1.5 squared minus 7 squared is. All right, cool kids, that was law of cosines. Yes, there were some really tricky application problems, but I'm hoping everything before numbers 13 and 14. If you want a picture of it, it's up there for 30 more seconds. I'm hoping everything before 13 and 14 wasn't that bad. So, at the end of the day, law of sines, it's great for more angles than sides. Law of cosines, it's great for more sides than angles, but the ambiguous case is kind of like a in-between, and I think law of sines is better. Chris? Yeah. Oh, that one. Okay. Think old iPhone. Think old iPhone versus new iPhone. This guy's operating system that does the alpha y equals is unable to be transferred to that operating system because that's just not capable to handle the whole like subscript, superscripts that this thing does. As a result, if you're trying to use this guy and you're trying to do alpha equals y equals, you just need to put whatever that numerator is, like 1 plus 5 minus making that stuff, right? Divided by, make sure the whole denominator has that kind of stuff. And then, real quick, if you do a cosine inverse, because you have to do that sometimes, make sure that you have a numerator. Denominator, you need those extra parentheses in the front so that after you do the numerator denominator, all of it is in cosine inverse, or else it's going to give you errors all day. Yeah. Okay. That was 13, that was 14. Here we are, 6.3 vectors. Let's get reset. Let's get reset. We are talking about, you should already have that page written so I can fill it in really fast so we can move on. Vectors. Blessings be upon you.
Thank you.
Everyone take a moment to double check your mask. If you can touch your nose, your mask is not on. Thank you. And let's get it on. Trying to allow our classmates and ourselves to stay on campus as much as possible this semester, yeah? We doing okay? We ready for notes? Remember, I'm here during lunch, I'm here after school, I'm here during period 7 if you need some more troubleshooting on that homework that's due by 3:30. Ryan?
So, you know the questions for 6.2, will you test this on those possibly?
Will I what?
Test this on those?
Bearing will not show up on your test.
But like the law of cosine on 14, we have to do the inequalities, will that show?
14 you have to write inequalities? Did I just not copy some of that question? I don't think I saw any inequalities. Give me a second. What do you mean, bud?
Oh, sorry. I said like write an equation. Do we have to do that? Like on a test or something?
I probably wouldn't have like awkward unknowns. I would probably have numbers that you would be able to solve for. So this idea of having two unknowns is good in that you can see a relationship that's going to be true no matter what. Because this, this is the connecting rod right here. Is this a piston? Is that what that is? Come on, people that know the engine, right? Okay. The idea is as your engine is working, this is continually changing, right? Within a certain range. And then you have like this whole situation. So what's powerful about this in possibly future applications in like mechanical engineering is that you can model the relationship between x and theta that entire time as it's moving. And so I'm introducing you to that idea, but this class is not mechanical engineering, so I won't be requiring you to show me that you necessarily can build a formula from the law of cosines. I'm just exposing you to that. So that wouldn't be a test question. That would just be an exposing application problem at homework. Does that kind of make sense?
Yes, something similar to this, but not quite.
With numbers, maybe,
Yes.
but not with two unknowns. Two unknowns makes it powerful. Because algebra says I can relate something even though it's not always staying the same. Like that's the power of algebra, or the power of variables. But yeah, it won't be on a test. Okay, coming back. Here we go. 6.3. I know we all got distracted, but that's okay. Everyone's question is valid. Just don't let that derail the derail the class. Lucas is being a very safe father. No taking pictures, trying to get extra credit.
He let it down. Yes, he did.
I wanted to.
I mean, laying it down as if it's resting on his neck, but that's okay.
No. Like, set it down there.
Woo!
Yeah.
I want him to throw the baby
Bro,
up in the
Lucas,
air so I can
what points
take a
are
Hold on,
picture.
hold on,
I
hold
want
on,
support.
hold on. My room's supposed to be a safe place. Don't go taking away my room safety.
I just want him
But
to throw
yeah,
the baby up. in
Okay,
the
here we
air.
go.
He let it
They're keeping you on your
down. I
toes.
could have done
Yeah.
double extra credit.
Oh my goodness. This is Lord of the Flies all over again. So, coming back. 6.3, vectors in the plane. Pitting us against each other. Come on. Here we go. Vectors. What I showed you yesterday. Someone tell me the color of the only vector written on the screen. Drawn on the screen. Purple. Purple is the vector. So what is blue? Not magnitude. Magnitude is actually purple. It's the length of purple. It is a triangulation. Oh, anybody ever heard of triangulation? Triangulation? Someone Google triangulation or ask Siri what triangulation actually means. To triangulate something. Has the word triangle. Triangulation. You can say define : triangulation, or if you want to talk to Siri, have some fun and say good morning. What is triangulation? Ryan, what do you got?
Like, describe the person's use of threats of exclusion or manipulation.
Okay, that's one way. Any mathematical definitions?
Tracing and measurement of a series or network of triangles in order to determine a distance and relative positions of points spread over a crystal region.
Interesting. Now, this isn't quite so complicated as what triangulation sometimes is used for, but I am in some sense triangulating my vector. What does that mean? The vector itself is not a triangle. It's a purple line with an arrow on it to show direction. It has both direction and... Oh yeah, here it is, right there, right? However, I could, in a sense, triangulate, and it's not fully as far as, like, cell reception and stuff like that, trying to triangulate and find someone's location, but it is in a sense of breaking this down into its triangular pieces. So X and Y are triangular pieces that would lead to the purple vector itself. This is what we call, and you're going to have some more notes on it in the future, but I'm just kind of giving you the short and sweet version as much as I can. These are called the components of the vector. The X and Y are his components. And specifically, they would be his horizontal component and his vertical component. That would that would produce the overall result of the beginning to end of the vector itself. Some people call this taxicab geometry, in a sense. Like in the valley, if you were trying to get somewhere, question, how often are you going diagonally, like in a car to get somewhere? I want to get to, let's see, what would be that direction? If I was trying to get to Sharky's on like Reseda and whatever, Nordhoff, I was trying to get to Sharky's. I'm trying to think of what's something in that corner that's not somewhere else around here. It's McDonald's, but there's that one, but there's also that one. What? It's right next door. Fine, if we want to get to the Wiener Schnitzel, down on Nordhoff, I need to head that way. Question, can you get into your car, someone else's car, maybe Alexis would, she shouldn't, and just drive that direction? No! Why? There's no roads that way.
Alexis makes the
We live in the valley. So question, even though the direction of it is this way, what would we have to do instead? There, right? We would have to, in a sense, think about the horizontal and vertical components to get in the direction. If I was a bird, I could fly that way. But since I'm in a car and we live in the valley, we'd have to, if you live in Santa Clarita, you would go on these roads that like this. But anyway, coming back. Plum Canyon, right? Take that one up. Ooh, that swoops all over the place. McBean is brutal. Coming back. But in the valley, you're going to do this triangulation idea. So the idea is I can get from here to here in a... Wait. I've been talking about distance. Ready? We can also break down... Ready? I ask things multiple times because I have multiple people that are ignoring me. Ready? I can talk about a force in the same way. I can talk about a velocity in the same way. I can break it down into its individual components, much like I would breaking down the direction of something by how I would actually have to drive to get there. A vector is just the hypotenuse? Well, no, it's its own thing, but I could think about it like a hypotenuse of a right triangle where, I know it doesn't look perfectly right because I kind of write at an angle. If I was here, it'd probably be straighter. Anyway, I could think of horizontal vertical components like if you were to head due east and due north to go that northeast direction. Anyway, I'm breaking it down. Now, I want you guys to look at the picture. You don't have to necessarily write it down. I want you to look at a picture. We're going to consider which illustration is more accurate in just a second. But first of all, didn't we say, Lucas, actually, who's easier? Jackson, can you go turn off all the lights? Didn't we say there was a certain movie that might inspire greatness in this section? Yeah? That certain movie that might inspire greatness. Very funny. Let's have some inspiration before we keep going.
Or airplane.
Oh, sad days.
I'm applying for a new villain role, go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah! Check out my new weapon. Piranha gun! Oh, yes! Fires live piranhas. Never seen one before. Now you have my invention. You want a demonstration? Oh, ah! It's so difficult sometimes to get one back.
Okay, so when I asked you guys at the beginning of class, hey, what is a vector and what is it defined by? I was thinking at least some of you would remember a mathematical term that represents a quantity shown by both what and what, or showing both what and what? Direction with an arrow and magnitude with a how long. However, did you guys notice that I had something to do with roller coasters on the screen just a little bit ago? Why would I have roller coasters when I'm talking about forces and velocities? Hey, what do you feel when you're on a roller coaster? You feel some force, right? So to inspire us in that way, let's go ahead and watch one other scene. Just to inspire us, one other scene from the
Don't do that. No.
But we've never been, and it's the funnest place on earth.
Don't care.
Please! Oh, please! Please! Oh, come on!
Night one.
Come on!
Bye, have fun.
Sorry, dude. You can't ride without an adult.
I know the safety was a little sketch in that roller coaster. Won't lie. All right, coming back. I want you guys to then think about these pictures. Maybe even Google. Hey, do I give you a hint at the very bottom of the screen? Something to search if you want some inspiration. Which illustration is more accurate to forces that are acting on you, say, in a loop of a roller coaster? Which situation, which illustration, both of them are being taken from different books, different resources. Maybe even search, hey, anybody on Chrome, anybody on Safari, anybody Googling? A verb that didn't used to be around, but now very much, we all know what it means. Vector diagrams. Who's Googled it? Ryan, what do you think? Well, actually, it's like the left or the right. These are kind of like all showing different parts of the loop. Does that make sense? So left or right, what do you think? Then right. Who else wants to take a vote? I'm going to ask Ryan why in just a second. He's voting for the right. Anybody else going to take another vote? Say right too. What do you guys see on the right-hand one that makes you think it's more accurate?
On the bottom one, the top of the loop. Yeah, the gravity is acting on. That's very relatable.
On the bottom of the loop and on the top of the loop, gravity is what?
So it's like acting on it, so it's pushing it.
Yeah, because you're going to definitely be feeling that gravity. But actually, isn't gravity in every single situation?
Yes.
Right? What do you guys notice about gravity? Just because that's what Ryan Kukorian saw. What do you notice about gravity in every single one of these illustrations that's different than gravity? That's actually the one that can tell you which one's a better illustration. What's different between gravity here versus gravity there? Chris, what do you see?
Gravity's the black one.
Gravity is the light green one. It has a little subscript. It's hard to see. GRAV. It's the light green one. What do you notice about the gravity here versus the gravity there, and what that makes that a better illustration than this? But you guys did notice the triangles, and the triangles definitely help as well. What's bad about how they're showing gravity in the left-hand side? Or, why am I able to say that this one shows or illustrates vectors, whereas this one only shows direction? Which one's building off of each other? Yeah, but how is it? That's an excellent observation, but Johnny, can you put some more words to that? What do you mean building off of each other?
They're like showing the exact direction of where the forces have it's triangulation.
Yeah, exactly right. You're triangulating. Maybe the combined effect. Can I use that? Does that help? They're showing the combined effect of the different forces in order to result in that normal force. Wait, no. Hold on. What would be... I'm going to give you guys a term early. You ready? Which force do you think is the resultant force, aka the overall force, in these vector diagrams? Johnny noticed this whole putting together. Johnny noticed, and I brought in this whole combined effect. If you're putting together, if you're combining, think like a recipe, you're putting in ingredients and you're trying to get an overall finished result, what would be called the resultant vector or the resultant force? What color? Do you guys think it'd be black, red, blue, or green? Black is showing you two different forces acting. Those two forces are being taken and given colors. So I wouldn't say black. Black is kind of like, you're in the car, what's happening? Let's take that. You're in the car, what's happening? Let's take that. So right away, let's take out black. Black's just kind of like the beginning situation, like over here, and then we're taking those somewhere else. Blue is this interesting thing called the normal force, which is known as the perpendicular force, and it's the force of something on a surface. It's what force that surface is acting against that object. What am I talking about? When you're in a roller coaster car at the top of the loop, is there force from the car being on the surface, is there a force there? And the answer is yes, there is a force at work from that being against the surface. The surface is pushing back in a sense. However, inertia and different things like that are keeping you from falling out of the car. But the normal force is just like a perpendicular force of any object against a surface, of like that surface acting back. But that's not the combined effect. Centripetal motion, what? Yeah, centripetal force is what keeps it in, right? Somebody said it, you said it right, I just didn't want to give it to you right away. It is the red one, because the red one, if you can't read it, does anybody know what the word net means in like business or in physics? All of it put together. Net is like all of it put together. You can also kind of see it over here in a sense, but what I wanted to show you guys as far as the accuracy. This one shows me both, wait, what are the two components of vectors over here? Well, from Despicable Me or from even our notes, what are the two components of vectors? Direction. So, question, is direction being shown in these different forces on display? Yes. Why? Because there are arrows. Yeah, there are arrows. Gravity is always pointing where? Downward. Normal is always pointing where? Away from the, actually the surface, technically. Away from the surface or away from, I know you guys see it from the car, but the car itself is more perpendicular to the surface. And then the net force is, well, I don't know, what's the combined effect? This is probably the easiest one to see the net, because what is gravity plus the normal force? The net force. Because they're working perfectly together. If they're working at angles to each other, the net force is going to be that overall like hypotenuse, but it's not necessarily a right triangle. So it's the connection, we would say, from tail to head of the vectors. But anyway, it does show direction. There are arrows all over the place, but how does it show magnitude, whereas the one over here does not? How does it show magnitude, whereas the one over here does not? What was that guy I was having you focus on? Oh, it was, but before that, I was saying, what's the one that is rightly displayed here and wrongly displayed here? Gravity was the one I was trying to point your attention to. What's true about all of these gravities that is not true about all of these gravities?
Gravity. In the left and right side of the thing. It's like
They different
towards the side.
Exactly, Joey, say it. You guys are all making good observations, but that is the key. What did you say? Does gravity change based on where you are in a loop? No. And so this one's saying the gravitational force, as long as you're in like a certain location on Earth, because Earth is not a perfect sphere, but we won't talk about like the, anyway, that's more fine points of physics. The gravity is perfectly congruent, the exact same length. Over here, why is gravity longer? I don't know, it shouldn't be. Gravity doesn't change because you're on the side of a loop. If anything, I mean, maybe you put that there being like, I feel it more. I don't know. But anyway, no. Gravity doesn't change. So these differing lengths, it was just showing direction in this illustration. This was actually showing accuracy, and that gravity is the exact same number. And so in our notes, we put down that magnitude is shown by the length of the vector. And so one quick reminder, does a vector mean like a ray in geometry? Does a vector mean, hey, it goes forever in this direction? Yes or no? No, because a vector's length has purpose, has meaning as far as the how muchness, like an earthquake, the magnitude of an earthquake, the how muchness, the magnitude of the force, how fast is the velocity, how long is the distance. I need that length to have meaning. The angle has meaning and the length has meaning. So this length, hey, you wrote it in your notes. This length has this term, magnitude, shown by the length in a diagram. It's It's the how much of whatever quantity you're measuring, whether it's force, whether it's velocity, whether it's distance, and it has a special notation. So for a vector, oh wait a minute, this is new, this is interesting. Hold on. Why are there 2 letters for vector? I mean, over here we just had 1 letter. It was vector V. That was his name and everything. What do you guys think the P and Q are representing? Think back to geometry. Exactly. So what if we go back here and say, hey, we could have had it start at a point P and end at a point Q, and we could say vector PQ. I'm still talking about the purple line, just in a different way. So I can say something like the magnitude of a single letter, that's a vector. Or I can say the magnitude of a vector from an initial point to a terminal point. But long story short, that is going to equal the distance or the length or the magnitude, which could be found with a Pythagorean theorem of its components, right? With the Pythagorean of its components. Now, if I know its components, I can just say, oh, sweet, its horizontal component and its vertical component, throw it into Pythagorean. But if I don't know its components, then aren't I going to be having to figure out how much across and how much up or down it goes? But isn't that the exact same thing as the distance formula? If I know it's changing y, if I know it's changing x, if I know it's horizontal, vertical components, sweet, just throw them in. But if I don't know them, okay, fine. Now, if you notice, though, now it starts to get a little dicey because now you're like, oh, I have x's and y's everywhere. So most people don't talk about the components with an x and y because those are more just talking about the points. They might use something like a and b. So they might change this up and say, you know what, x's and y's, that's kind of more like the points themselves. So they might change this up, even though it means the same thing. And instead of putting x and y, they could put a and b, and it would mean the exact same thing. I'm just talking about, like, what's the change in x's if I have, like, an x1, y1. A is the distance between the x's. Oh, my x2, y2. So I could have specific points depending on that. I could just call whatever those distances are, A and B. That works as well. But what we just saw then is that we could also say, well, who are these guys? These guys are x2 minus x1 and y2 minus y1. If I ever needed to find them, that's how I find the components. Whatever. Subtract the horizontal distances, subtract the vertical distances, review from before. But I could write them different ways and they mean the exact same thing. To find the magnitude, I just have to find the length. And to find the length, if I know the triangulation, if I know the horizontal vertical components, then I'm good to go. Something pretty powerful. You might not realize its power unless you were to go deep in vector diagrams, which we probably won't do. Not too deep anyway. But it is very helpful that vectors can be equal but can be shifted and moved. They don't have to stay in the same position, which is really helpful for things like this. These vector diagrams were possible because I was allowed to say, if this is the normal force, I can move it as long as I keep the exact same length and the exact same angle. I can move it to go be combined with gravity, which is what they did here. They were like, in order to find the net force, in order to find the overall result, I need gravity to kind of like flow into normal, and then I can tell the overall result from beginning to end. Or over here, same thing. I could say, take your gravity, take your normal. I could put my gravity, have it flow into normal, and then know my overall results. I can move my vectors around. I don't need them to stay in this like picture over here. I don't need it to stay looking like this. I can move it so that I can have them flow together. This one, they shifted him back and had the exact same thing, but over here, so I could follow the flow, one through the other. An addition of vectors will be the same, whether you have blue plus green or green plus blue. You'll get the exact same vector. Once again, it's not so much about positioning, even though that's helpful to see. It's more about what is the rotation, what is the direction, and what is the, oh, hey, yeah, direction and magnitude. This just says you're allowed to move them. So allowed to be moved. As long as you keep the same direction and the same magnitude. And if we're trying to actually find that resultant force, how we are going to move is we are going to move so that they can flow head to tail. We want to be able to have, like, start at the beginning of one vector to its end, to its arrow, and then have it go straight into the tail of another vector to its head. And so what I didn't get to label back here is that we do technically have other ways of talking. This could be the head of the tail. Wait, head to tail. No. Tail of a comet is what comes behind. The head, silly. And then its tail, like the tail of a comet, is what comes behind. There we go. The head is the arrow part, the tail is the other part. I mean, there's a lot of different pieces of vectors. I'm just kind of giving you like different ways of thinking about them. T and Q, X's and Y's, heads and tails. To get that overall result, we have to put the vectors, if we were making a vector diagram, which uses a lot of geometry. To find the overall resultant, we take our pieces, we move so that they flow head to tail, and that can give me a result. And then that vector could be net force, it could be net velocity, it could be net distance from beginning to end of a situation. Now, I'm giving you some stuff early, in some senses, just trying to like pack these first few slides full, and then we can just kind of play with the different things that we might be given. But Baron, go ahead, what's up? Yeah. Resultant or net vector. So if we want to get the overall result, like the red ones in the roller coaster, we just need to take all of our little piece vectors and like have them flow head to tail through each other, and then connect the very beginning to the very end. Right.
So like the vector is aligned with the like a distance amount and the direction. So what is the difference between that and a regular line?
Well, regular line has no direction. And we've never, like you, I don't think any of you have ever used like line segment AB to talk about like how fast something is going. Up to this point, you've probably just said how far or how long, right? But to say how fast or how much force, that's new to you.
Because like every line that I've graphed before is a vector.
No, because there's no arrow on it. So the question is, like this line that you graphed, was it working against or was it working for? Were you going southwest or were you going northeast? No idea. So you've had distance, you've had magnitude before, but you haven't had direction. Most of you. Like you've had array, but array was something that goes on forever, right?
Yes.
So that's a little different because we need to have a finite length to actually be able to have it model what we need.
I was just thinking like in algebra, the equation mx plus b, like the line equation, it had a distance, but it also was shooting the guys in the direction. Right?
But that's only if you happen to make this your first point and that your second point. What if you graphed that one first and then this one?
Which could be.
Right. So there is no like defined direction of it. You might have had a direction that you graphed it, but that doesn't mean that was the direction that was assigned to it or that it was modeling.
So how do you determine the direction of the vector?
Oh, good question. First of all, it could be given to you. First of all, it could be given to you. Second of all, you could tell from its name. These two vectors have been given to you in the sense that they've both been shown on a graph. You can see the arrow where it is, but you can also see a vector like its beginning and ending where its arrow should be by the order of the letters. So if I have point R and if I have point S, if it's written RS, then it's going from R to S. My arrow is where it's supposed to be. I could not write it SR because that would be going the other direction. So to model this one, I have RS. And I'm trying to do RS versus PQ. So one way it's in the picture, but another way if they give you points, then you can know the beginning point and the ending point. And the arrow should be, like the notation shows, the arrow should be on that last or final point. We call it terminal in physics.
Symbol on top of vector symbol, like the arrow.
Mm-hmm. Like we saw last time, yeah. Remember, the book is going to use bold letters, but bold letters are not something that we can handwrite, which is why we put handwritten, put an arrow on top. And that shows that it's a vector. Now, if I wanted to test their magnitudes, I'm going to make them two different colors just to make it a little bit easier. If I wanted to test their magnitudes, they look equal, but without you guys getting out protractors and getting out rulers, how can you mathematically show they're equal? Well, I can show they're equal by, let's see, RS is the red one, by figuring out RS's magnitude, which says, hey, what's the square root of? Well, horizontal, 4 minus 1 squared plus vertical, 4 minus 2 squared. I'm just doing the Pythagorean theorem. How far over to how far up? And 9 plus 4 is 13. This guy is square root of 13 long because of the distance formula. Those of you guys that are talking, if you have questions, I would love to hear them. And if you don't, you probably should be focusing and not distracting the people around you. P and then Q. His magnitude. How far over would be his x2 minus his x1. How far up would be his y2 minus his y1. Hey, guess what? 9 and 4 is also root 13. I have just shown that they have the same what? I have just shown that they are equal in what way? Yeah, they both have the same magnitude. However, for vectors to be equal, I not only need the same magnitude, but what else do I need? The same direction. Direction you can show a couple different ways, but some ways that some people have shown it. Technically, you should use thetas, but we'll talk about thetas in a little bit later. Probably the easier way for you guys to see it is, first of all, where are the arrows? Are they pointed the same way along the vectors? The answer is yes. But second of all, are they at the same rotation? And one easy way to check that is with slope. The slope of the line, is it the same? If it is, if they are parallel, and as long as their arrows are going the same direction, we can say yes. So we already figured out the rise of these two guys when we subtracted our y's, and the run of these two guys when we subtracted our x's. Same thing here, we figured out our rise of these two guys when we subtracted our y's, and our run of these two guys when we subtracted our x's. Since their slopes are the same, and the arrows in the same place, we can say yes, they also have the same direction. In a way. And why is that? Well, that's because when I'm doing the change in y over the change in x, technically that's measuring this side, like the triangulation kind of this vector, or breaking it down into its components is a bit more of a physicsy way of putting it. When I break that down, when I figured out that I had 2/3, 2 is the opposite, 3 is the adjacent. Technically, it's only possible for those two to be equivalent first quadrant angles in that their little rotation are both under 90 if the theta is the same. And I can even actually find what that theta is if you wanted to literally compare their angles by doing a quick tangent inverse. By looking at them, they're both going to be that little first quadrant angle that I would find, and it would be the same thing. So I'm kind of cheating and not doing the work of finding the nasty angle and just saying, like, okay, of course they'll be the same. Right.
So, to figure out the direction of the school, you figure out the slope and then what?
The slope indicates, right? The slope indicates that they have the exact same rotation because they have the exact same rise over run. Doesn't that also mean they're parallel? So the slope shows you that they're parallel. If I wanted to, I could find the angle as to what that rotation is using tangent inverse. But since I have the picture, I see the arrows going the same direction and I see the slopes are the same. So I know that the directions are equivalent.
How do you know they're pointing same way.
Oh, they gave me the picture and I looked at it. I know they're parallel, which means they have the exact same angle, and the arrows are headed the same way. So, this idea of breaking down a vector. Why am I putting the arrow where I'm putting the arrow based on what you see on the screen? So, Ryan, this is kind of your question, right? How do you know where the arrow is if it's not drawn for you? How did I take one look at what I saw? And I remember that Jamboard doesn't let me put little arrows on top, so give me 1 second to put little arrows. But how did I know the arrow goes where I put it? Why wasn't it the other way? The initial point was R because it came first, and the terminal point is S because it comes second. So Ryan, this is another way to think about it as far as your 2 points. That second point is where the arrow always is. Oh, you know what, guys? I think we already wrote all this down. You could write it down again if you want. I already gave you guys all this information. In the sense that you guys should already have the x2 minus x1, y2 minus y1. So therefore I could have my a squared plus b squared equaling my distance formula. I just wrote it early. I don't think you guys need to write it again. But make sure that you do have the terminology for these guys. The terminology is the component form. Component form says I can take a vector and I can break it down. Actually, to be honest, technically it's just the horizontal distance and the vertical distance. But I know the arrow because I know that it's always going to be at that final point. Something interesting about like some vocab. So the zero vector. It might seem kind of silly to you, but a zero vector is like I'm just a point. He hasn't gone anywhere. His over and up and down is just 0, 0. But a unit vector is a little more interesting. A unit vector is a guy with a length of 1, which means he could have a length of 1 up. He could have a length of 1, oh, I didn't flip it, sorry, over. Or he could have a length of 1 out. My unit vector could go up 1, that'd be a length of 1. He could go over 1, that could be a length of 1. He could go back 1, that could be a length of 1. He could go down 1. All of those are unit vectors. But I could also go out 1. Oh my goodness. The unit vectors are going to be all the vectors that hit up against the unit circle. So there's not just one unit vector. The unit vectors are all the ones that would hit around the unit circle. So I could have drawn more. I just gave you guys a couple examples. Unit vector is a scale back vector that says I have a length of 1, but I'm going the right direction. So it can have a lot of different components. Once again, you guys are good as far as all of that. We already wrote all that down. But I do want to make sure that you guys have the actual name of these little side carrots. Hey, do you have side carrots on your keyboard if you had to write them? Yeah, you can use the greater than or less than symbols, or you might have in your calc pad like some option of like a different type of parentheses or brackets. Ryan Noonan, what's up, bud?
Sorry, what does this side like carrots mean?
Oh, that means component form. I gave a name to what I showed you earlier. And it's a breaking down of a vector to not just be like its purple line, but to be like its blue pieces. So then basically, oh, hey, I kind of put it here. Huh? These are the components, or I could say, if it helps you guys, the components comprise the component form.
So it helps show direction.
Well, actually, it shows everything because it'll get you to the final length, and it will get you, as long as you know that this is beginning and that's ending, it'll also show you direction. Yeah. Fine.
So when you try to figure out the direction, you just look at the name, like RS.
If it has the points. Yeah. It can be named with a lowercase letter, which wouldn't really help you much. It could also be named with 2 points. If it has 2 points, you can see where that ending is, and that will be where the arrow is.
I use the bathroom.
So along the lines of Ryan's question, if you were to be given something like this, it would be impossible to do.
Oh, you don't know which one's which.
Exactly. So what has to be true? Ready? To know what kind of vector it is. You either need to have them give you an arrow, which once again Jamboard didn't let me show. So they either need to give an arrow or they need to give some sort of name like, hey, it's vector B, well, AB if I want to look the same. If they tell you its name with points, you'll know to put the little head right there or the arrow of the vector right there. Or it needs to be in the picture itself. Does that kind of make sense, guys? That was probably best for Ryan because he was the one asking those questions and he just left the room. But yeah, it either needs to be shown in the picture or it needs to be somehow given in the information. So this picture was incomplete, but that was because Jamboard didn't let me show the arrow, so I have it on there now. Good. So if this is the direction that the arrow is going, my vector AB is that little B guy that they're asking me for. What would you guys be able to fill in for his components? What direction would you be doing your subtracting? Remember, I just want to go over and up, kind of like rise over run. I just want to go over and up. So Ryan, what do you think? Because you did the terminal point, right? Minus the initial point. So remember that when you are trying to find the component form given initial and terminal, make sure to do your terminal minus initial. I need the ending minus the beginning to get my signs right, my positives or negatives right. So my x2 is my terminal point minus my x1 is my initial point. That is 3. Somebody else. Mimic the procedure for the y's. 2 minus 4, which is negative 2. Question. From beginning to end, do I go over a positive 3 and down 2? From beginning to end, do I go right 3 and down 2? Yes, I go right 3 and down 2, so you guys have done it correctly. Right 3, down 2. That will get me to the end. So if you guys want to have like a more physicsy way of writing this, we could say something like the final or the terminal, usually we call it final in physics, minus the initial, and the final y minus the initial y. There are ways of putting zeros, but we won't worry about that. So you have the component form. Now how do we figure out the length? It's just applying some of the stuff we've done with rise and run, basically, right? But what would the length be? Now remember, there's new notation. The length says, hey, give me double lines. Like double absolute values, kind of. How do I find the length of any hypotenuse of a right triangle? Oh. A squared plus b squared is c squared. I need a square root, right? What'd you guys just find? Well, you just found for me what A is, and you found for me what B is. So therefore, wouldn't I have as my final answer? You guys PEMDAS it. What's 9 plus 4?
13.
Okay, it just happens to be a popular number today. Don't just go putting root 13s on every WebAssign problem. That probably won't help. Just happens to be a popular number today.
So that would be the magnitude.
That would be the magnitude.
Which is the magnitude is just
The how muchness or the length, which can denote force, it can denote speed, it can denote all sorts of things. Now, if you guys remember from last time, this is where we're going to end, is this slide right here. If you remember from last time, I said that we have a minimum date on Friday, and 6.3 is a bit of a doozy, and I need to be able to finish on Friday 6.3. So we are doing 6.3 on Friday. The 6.3 will not be due until Monday, which is a chapel day, I believe. But what I want to show you is the power of components. Because with components, if I was to do something like, P.S., this is going to be called the resultant, which is adding two vectors together. If I have their components, it's easy cheesy. Oh my goodness. If I have the components, it's easy. If I have the angles, it would be rough. If I have the components, all I have to do to find the resultant is say, hey, what happens when? But if I kept it like this, I would have to do some crazy geometry and say, hey, I need to move that, I need to use parallel lines, and I need to connect these, and then I would have to figure out some sort of like law of sines and law of cosines and parallel lines. We are going to avoid all that if we do components instead. And that's where we're going to pick up next time. Bye guys, I'll see you later. And I'm going to go double check that your homework deadline is after the weekend like it's supposed to be.
Have a nice day.
Thanks.